Hello Calc 3 and welcome back to another video. In this video we'll be covering section 14.7, the last section for chapter 14, on extreme values and saddle points. So ultimately the goal of this section is to generalize the notion of local extrema and absolute extrema from Calculus 1. So remember that in Calc 1, we used the derivative to find points at which some function f of x may have a local minimum or local maximum. So you might recall that we could take a function, take the derivative and set the derivative equal to 0, and we got some critical points, and then we could examine those critical points to see if we had relative extrema at the different critical points that pop up. And I actually gave you a question related to that concept on the last exam. So in this section, we're going to generalize that methodology to functions in two variables that describe a surface in space as opposed to a curve in the plane. So for single variable functions, we find local extreme values by searching for points that have a horizontal tangent line. So remember that I have this curve, which is green inside of the plane here. And then I've picked 2 points. The point on the left is going to be a local maximum, and you can see that the tangent line is horizontal through that point. And the point on the right is a local minimum, and again you can see that the tangent line is going to be horizontal. So the derivative at both of those points is going to equal 0, and we can use certain tests, remember the first derivative test and the second derivative test, to determine if the critical values are local minima or local maxima, or in some cases, neither. So they're not local extrema at all. In the case of functions of two variables, instead of searching for points with a horizontal tangent line, we search for points that have a horizontal tangent plane. So this time we have a function f of xy. It's describing some surface in space. And our critical points are going to be points where the tangent plane to the surface at that point is horizontal, or perpendicular to the z-axis would be another way to describe it. And then we're going to determine whether these points are extrema through the use of some tests. So we're going to call critical points on the surface points on the surface that have a horizontal tangent plane, and then we're going to develop some tests to determine whether those points are extrema. So let's get on to some definitions here. If we let f of xy be some function defined on a region R containing the point AB, then f of AB is a local maximum value, I should probably underline that, local maximum value of f, if f of AB is greater than or equal to f of xy for all domain points xy in an open disk centered at AB. So if you want to think about this pictorially, you can look over to the left where I have this little diagram here. So we have a region R, which is the enclosed loop in red inside of the plane on which our function is defined. And then we have a purple point inside, which is the point AB. And f of AB is going to be a local maximum value if I can draw a little disk like I have in dotted purple line there. If I can draw that little disk such that if I take any point inside of the disk, f of AB is going to be greater than or equal to f at that point. So that's the definition of a local maximum. And f of AB is a local minimum, and this definition is pretty similar. It's a local minimum value of f if f of AB is less than or equal to f of xy for all domain points xy inside of some open disk centered at AB. So we can refer to the same diagram over here. The only difference is that this time I'm trying to draw a small disk around the point AB such that if I take any point inside of that disk and plug it into f, the value is going to be greater than or equal to f at AB. So another way to think about this intuitively is that local maxes will correspond to mountain peaks in our surface, and local minimums will correspond to valley lows in our surface. And I do have a picture which I stole from the textbook because I definitely know that I can't draw that, showing some local maximums and a local minimum. So again, look or notice that this local minimum is kind of like the bottom of a valley in the surface, and these local maximums are kind of like the peaks of mountains along our surface. So this should give you an idea of what these local maximums and local minimums look like. And like functions of a single variable, the key to finding the local extrema is the first derivative test, where the first derivative test refers to what the partial derivatives are going to be when we plug in a point that is a local extrema. So let's get on to that theorem here. So we're going to call this theorem the first derivative test for local extreme values because that's what the book calls it. So if we have a function f of xy, and if it has a local maximum or minimum value at an interior point AB of its domain, and if the first partial derivatives exist at that point AB, then the partial derivative with respect to x at AB is going to equal 0, and the partial derivative with respect to y at AB is going to equal 0. So this is similar to the fact that if we have any kind of relative extrema with a function of one variable, like functions from calculus 1, then the derivative at that point is going to equal 0. Which ends up being why we find critical points in the first place in Calc 1. So notice that the equation for the tangent plane at the point AB is given by partial x at AB times x minus a plus partial y at AB times y minus b minus z minus f of AB is equal to 0. So this is actually an expression that we came up with in the last section, 14.6. So assuming that AB is a relative extrema, then we know from the theorem above that the partial derivative with respect to x at AB and the partial derivative with respect to y at AB will both equal 0. And we can use this fact and plug back into the equation for our tangent plane. So now we have 0 times x minus a plus 0 times y minus b minus the quantity z minus f of AB is equal to 0. Well, these terms are both going to go to 0, and we're just left with the equation z is equal to f of AB, where f of AB is just some constant, whatever pops out of the function when I put in AB. And this is the equation for a plane that is perpendicular to the z-axis, or another way to think about it is a plane that is horizontal in space. So the equation of the tangent plane is z equals f of AB, meaning that the tangent plane is horizontal, which is what we expected. So the fact that the tangent plane is going to be horizontal at our relative extrema is analogous to the fact that the tangent line is horizontal to our relative extrema in the case of single variable functions. So now let's move on to another definition. It should look pretty familiar. We're just generalizing from Calc 1 again. So if we have an interior point of the domain of f of xy, where both f sub x and f sub y are 0, or where one or both of f sub x and f sub y do not exist, then we're going to call that interior point a critical point of f. So if we have that the partial derivative with respect to x and the partial derivative with respect to y at some point are equal to 0, then that point is going to be a critical point. Or if one of the partial derivatives with either respect to x or y does not exist at the point, we're also going to have a critical point in that case. So here's just some important information that's going to come in handy as we go through the video here, especially towards the end. The extreme values for a function f will occur along the boundary of the domain of the function f or at critical points. And I should maybe specify that I'm talking about the absolute extreme values. So remember that if we have a function in two variables, then the region on which that function is going to be defined, again, is going to look something like this. Who knows what it looks like? And this statement here is saying that the absolute extrema are either going to occur at some critical points that lie inside of the region. Maybe it would look something like this. Maybe we'd have 4 different critical points. Or the absolute extrema have to occur somewhere along just the boundary of the region. So this is an important fact when we're talking about a closed bounded region. So this is analogous to the fact from Calc 1 that the extreme values of a function f of x on the closed interval from a to b must occur at either critical points inside of the interval from a to b or at the endpoints of the interval from a to b. And hopefully you're familiar with this now because again, this was an important part of question, I think, 11 on exam 1, where we had to find some extrema for the speed function. And now an important note before we move into the next definition. Remember that from Calc 1, just because a point was a critical point didn't necessarily mean that that point was going to be a local extrema. Sometimes that point was an inflection point, and we found that the rate of change of the function did not switch from negative to positive or from positive to negative at our point, so we didn't have a relative extrema. Well, the same kind of phenomenon can happen for functions of 2 variables. So that leads us into this next definition. If we have a differentiable function f of xy, then that function is said to have a saddle point at a critical point AB if in every open disk centered at AB there are domain points xy where f of xy is greater than f of AB. And all this really means right here is that this tells us that f of AB is not a local max, and domain points where f of xy is less than f of AB. And this tells us that AB is not a local min. So what this is saying is that we have a point, it's a critical point, but the critical point is not a local max and it's not a local min. And in that case, we're going to call the point a saddle point. So the point AB f of AB, notice now we have a point in 3 dimensions. On the surface, z equals f of xy is called a saddle point of the surface. And I have some pictures to correspond to what we're talking about here. So a saddle point is ultimately just an example of a critical point that is not a local extrema. I have 2 different pictures on the right of saddle points, specifically at the origin. So notice that if you look at, let's see if I can draw something nice here. If you look at this saddle point here, if you were to draw a tangent plane to that saddle point, the tangent plane is still going to be horizontal. It's going to be perpendicular to the z-axis. But you can see that the function curves down as you go along this direction, and the function curves up as you go along this direction and this direction. And because of that, no matter how small of a disk we draw around that saddle point, we're always going to have some points that have a bigger value of f and some points that have a smaller value of f. And for that reason, the saddle point is not going to be any kind of relative extrema. So let's move on to an example. Let's say that we want to find the local extreme values of some function f of xy is equal to x squared plus y squared minus 4y plus 9. So we know that the local extrema are going to be critical points. And to find those critical points, we start off by taking the partial derivatives with respect to x and y. So f partial x is equal to 2x, and f partial y is equal to 2y minus 4. As always, if you want to double check that, you can pause the video and just make sure the calculation is correct. And now we can set f sub x equal to 0 and f sub y equal to 0, and then solve to find our critical points. So 2x is equal to 0 implies that x is equal to 0, and 2y minus 4 is equal to 0 implies that y equals 2. And so we only have one critical point in this case, and that critical point is 0, 2. And now notice that if we take our critical point and we plug it into the function f, we get f at 0, 2 is equal to 0 squared plus 2 squared minus 4 times 2 plus 9, which is ultimately equal to 5. And now we need to show that this point is either a local max or a local min. And we haven't really talked about tests to show when a critical point is some kind of relative extrema, but in this case we don't need tests. We can just do a little bit of algebra to show it. So notice that if we take our function f of xy and we write it out again, so it's x squared plus y squared minus 4y plus 9, then we can complete the square with this y squared minus 4y here. And ultimately the function can be rewritten as x squared plus y minus 2 the quantity squared plus 5. And now notice that x squared is always going to be greater than or equal to 0, regardless of what x you put in. And y minus 2 squared is always going to be greater than or equal to 0, regardless of what y value you stick in. And for that reason, f of xy is always going to be greater than or equal to 5 for all xy in the domain. And in this case, the domain is all points xy. And for this reason, since the function at every other point in the domain is going to be greater than or equal to 5, we know that the point 0, 2 is a local minimum. But this is somewhat of a rare occurrence here. Typically, we're going to use some other rules to determine whether a critical point is a local extrema, and if it is, whether it's a local max or a local min. So that's what we're going to move into next. We now develop a better way to determine whether a critical point is a local minimum, a local maximum, or neither, a saddle point. So this is probably the biggest theorem for this section here. This is the thing to pay a lot of attention to. So we're going to call this theorem the second derivative test for local extreme values, because again, that's what the book calls it. Suppose that we have some function f of xy, and its first and second partial derivatives are continuous throughout a disk centered at AB. And also suppose that the partial derivative with respect to x at AB is equal to 0, and the partial derivative with respect to y at AB is equal to 0. So this is just saying that our point AB is a critical point. Then f has a local max at the point AB if f sub xx, so notice here that this is a second order partial derivative, if f sub xx is less than 0 and f sub xx times f sub yy minus f sub xy squared is greater than 0 at the point AB. So I know that this expression here is kind of obscure, but it's a very important expression and something you're probably going to want to memorize. Likewise, f has a local minimum at the point AB if f sub xx is greater than 0. So notice here f sub xx is greater than 0 as opposed to less than 0 for the local max, and f sub xx times f sub yy minus f sub xy squared is greater than 0 at the point AB. So when we evaluate this expression at the point AB, we get something greater than 0. Now for the third point of our test here, f has a saddle point at the point AB if that f sub xx times f sub yy minus f sub xy squared term is less than 0 when we evaluate at AB. So notice that in case 1 and case 2, that expression was greater than 0 in both cases. But now in the third case, we have that expression is less than 0. If that expression is less than 0, we always have a saddle point. And finally, if this infamous expression f sub xx times f sub yy minus f sub xy squared is equal to 0 at the point AB, then the test is going to be inconclusive. So this last point 4 here is kind of similar to the second derivative test from Calc 1, where we got that the test was inconclusive if the second derivative was equal to 0 at a point. So this infamous expression, this f sub xx times f sub yy minus f sub xy squared, is called the discriminant. or the Hessian of f. So I'm probably just going to call it the discriminant. So when I say the word discriminant from now on, that is what I'm talking about. You can also notice that the discriminant is actually equal to the determinant of a matrix, which is given by f sub xx, f sub xy in the first row, and f sub xy, f sub yy in the second row. It's just a little interesting piece of information for you. You could remember the formula for the discriminant by remembering that it's the determinant of this matrix if you wanted to. But let's move on into an example now. So let's say that we want to find all of the local extrema of the function f of xy is equal to xy minus x squared minus y squared minus 2x minus 2y plus 4. So we want to find all these different extrema, and we also want to determine whether those extrema are local maxes or local mins. So let's get into it here. The first thing we want to do is take the partial derivatives with respect to x and y. So the partial derivative with respect to x is equal to y minus 2x minus 2. And the partial derivative with respect to y is equal to x minus 2y minus 2. Again, you can pause the video and check if you'd like to. And so we're going to set both of these expressions equal to 0 to find our critical points. So when we set the partial derivative with respect to x equal to 0, we get y minus 2x minus 2 is equal to 0. When we do the same for the partial derivative with respect to y, we get x minus 2y minus 2 is equal to 0. And using equation 1, we can solve for y. So we know that y is going to equal 2 plus 2x. And then we can substitute into the second equation. And we get x minus 2 times 2 plus 2x minus 2 is equal to 0. And doing a little bit of algebra here, we end up finding that x is going to equal minus 2. And because x is equal to minus 2, we know that y has to equal minus 2. And so the only critical point is going to be the point minus 2, minus 2. And now that we have that critical point, we're going to determine whether it is a local extrema. So to do so, we'll use this second derivative test that we have up here, the theorem that we just developed there. So f sub xx is equal to minus 2. Maybe I should bring up the first partial derivative with respect to x up here. So you can verify that f sub xx is equal to minus 2. F sub yy is equal to minus 2 as well. And f sub xy is equal to 1. So f sub xx at our point minus 2 is going to equal minus 2, which is less than 0. So far it looks like we're fitting into case 1 here. But now we need to make sure that the discriminant is greater than 0. So let's calculate the discriminant now. F sub xx at minus 2 times f sub yy at minus 2 minus f sub xy at minus 2 squared is equal to negative 2 times negative 2 minus 1, which is equal to 3, which fortunately is greater than 0. So using the second derivative test, this falls into category 1, meaning that f has a local maximum at the point minus 2, minus 2. And if we take that point minus 2 and plug it into our function, we get that f at minus 2 is equal to 8. So this would be the value of the local maximum here. And the local maximum occurs at the point minus 2. Okay, so let's move on to another example here where we find a saddle point. So let's say that we want to find the local extreme values of the function f of xy is equal to 3y squared minus 2y cubed minus 3x squared plus 6xy. The process is going to be the same as before. I just wanted to go through this example because ultimately this time we're going to find a point where the discriminant is negative and we have a saddle point. So let's get into it here. So the partial derivative with respect to x will be equal to minus 6x plus 6y. The partial derivative with respect to y is equal to 6y minus 6y squared plus 6x. And we're going to set both of the partial derivatives equal to 0 to look for critical points. So we have minus 6x plus 6y is equal to 0, and we have 6y minus 6y squared plus 6x is equal to 0. Well, the first equation tells us that x has to equal y at any critical points. And we can substitute y for x into the second equation and get the equation 6y minus 6y squared plus 6y is equal to 0. Do a little bit of algebra here, factor out a y, and find two solutions to that equation. So we have the solution y is equal to 0 or y is equal to 2. So ultimately this will give us two different critical points now. If y equals 0, then x is equal to 0, and if y equals 2, then x is equal to 2. So we have two critical points. We have the point 0, 0 and 2, 2. And now we want to determine whether these critical points are local mins, maxes, or saddle points. And to do so, we're going to need some second order partial derivatives. So f sub xx is equal to minus 6 everywhere. F sub yy is equal to 6 minus 12y. And f sub xy is equal to 6. And now let's first worry about the point 0, 0. So f sub xx at 0, 0 is going to equal minus 6, which is less than 0, since f sub xx is always equal to minus 6. And f sub xx at 0, 0 times f sub yy at 0, 0 minus f sub xy at 0, 0 squared, or just the discriminant at 0, 0, is equal to minus 6 times 6, minus 36, and this is going to give us minus 72, which is less than 0. So here the discriminant is going to be less than 0. And because the discriminant is less than 0, regardless of the value of this f sub xx at 0, 0, we know that we have a saddle point. So this point fits into case 3 in our second derivative test. And now we can look at the point 2, 2. So f sub xx at 2, 2 is equal to minus 6, of course, since f sub xx is always equal to minus 6, which is less than 0. And in this case, the discriminant at the point 2, 2 is equal to minus 6 times minus 18 minus 36, which is greater than 0. So in this case, the point 2, 2 satisfies case 1 from our second derivative test, so that f has a local max at the point 2, 2. And if we take that point 2, 2 and plug it into our function f, we find the value 8. So one of the local maximums for the function f is going to be 8. And in this case, it's the sole local maximum, and it occurs at the point 2, 2. And now we can move on to the last section for this video. So in this last section, we're going to take some of the information that we've developed about finding relative extrema and combine it with a few more pieces of information so that we can not only find relative extrema, but absolute extrema on closed bounded regions inside of the plane. So I mentioned previously that the absolute maxima and minima must occur at either critical points, so critical points inside of the region, or on the boundary of the region over which our function f of xy is defined. So if we want to find the absolute max or min of some function f of xy on R, there are three different things we need to do. So we need to find all of the critical points in the interior of R, and then we need to find the boundary points of R where f has a local maxima and minima. And thirdly, we have to evaluate f at all the points that we found. So in steps 1 and 2, we're going to collect all of those points at the end of the process, evaluate f at all of those points, and then the maximum value of f over these points specifically is going to be the absolute maximum of f over the entire region R, and the minimum value of f is going to be the absolute minimum of f over the entire region R. So let's move into the final example for this video here, where we find some absolute extrema of a function over a particular region. So we want to find the absolute maximum and minimum values of f of xy is equal to 2 plus 2x plus 4y minus x squared minus y squared on the triangular region in the first quadrant bounded by the lines x equals 0, y equals 0, and y equals 9 minus x. So when you're given a problem like this, the best thing to do right away is probably just sketch what that region R is actually going to look like. So in this case, our region, which I'm going to call R, looks like a triangle in the first quadrant. So we have the three vertices of the triangle will be the point 0, 0, the point 9, 0, and the point 0, 9, which I've labeled as O for origin, and then the point A and the point B. And so this will give us a good idea of what that region is going to look like, and it will be important as we move on here, finding the critical values along the boundary of our region here. So again, the first step is to find all of the critical values within the interior of the region R. So this ends up being, I think, the easiest of the steps. We're just going to apply the methods that we've developed in previous parts of this video here. So we're going to take the partial derivative with respect to x, and we get 2 minus 2x, and the partial derivative with respect to y, which is 4 minus 2y. Again, you can pause the video and make sure that that's correct and makes sense. And then we can take both of the partial derivatives and set them equal to 0 to look for critical points on the interior. So we have the equations 2 minus 2x is equal to 0 and 4 minus 2y is equal to 0. Well, the first equation gives us that x is equal to 1. The second equation gives us that y is equal to 2. So there's only one critical point, and that critical point is going to be 1, 2. And it is important to notice that that critical point does in fact lie inside of our region R. So if I was going to plot it up here, I guess it would look something like right here, that purple point that I'm drawing. If that critical point is not inside of the region R, then we're not going to consider it when we look for absolute maximum and minimum of f as specifically inside of that region R. It's just going to be a point that we discard. We don't care about it. So make sure that that point is actually inside of the region of interest here. And now the second step here, which is much more involved and unique to these kind of problems in higher dimensions than we saw in Calc 1. So now we're going to look specifically at the boundary of our region R, and we're going to find extrema along each edge of R. So notice that R is a triangle. We can split it up into 3 different edges, which is why I split part 2 up into 3 different parts, A, B, and C, where we're going to consider each edge one at a time. So let's start off with the line segment that goes from the origin to A. So on that line segment, x is going to vary from 0 to 9, but y is always going to equal 0 since we're traveling along the x-axis. So in that case, if we take any point on that line segment and plug it into our function f of x, y, it's going to equal f of x0 because we know that y is going to equal 0 along that line segment. And if you check with our function up above here, f of x0 is equal to 2 plus 2x minus x squared. And now this is just a function in x here. So we can take the derivative of that function with respect to x. So we can evaluate f prime of x0. And we know from Calc 1 that the absolute extrema for this now single variable function f of x0 is either going to occur at the endpoints of the interval, so at x equals 0 and x equals 9, or a critical value that's inside of that interval. And to find the critical value, we take the derivative of f prime of x0, which is equal to 2 minus 2x, and we set that derivative equal to 0. And in this case, when we set it equal to 0, we find that x has to equal 1. So there is one critical point along that line segment from the origin to the point A, and that critical point is going to be 1, 0. So now we have 3 different points of interest that we're collecting here. Remember that before we get to step 3 of the process, we're really just trying to collect all of the points inside of the region that could be contenders for absolute maximums and absolute minimums. So in this case, we have our endpoint of the line segment, so we have the point 0, 0, and 9, 0, and then we have the sole critical value along that line segment, which is going to be the point 1, 0. And now we can move on to the next part of the boundary of our region R. So we're going to look at the line segment from the origin to B. And that line segment goes directly up. So let me go back up to the picture for a second. We're looking at this line segment on the left now. So it's going to go directly vertically, meaning that x is going to equal 0 at all of the points on that line segment, and y is going to vary from 0 to 9. So this looks pretty similar to the last case, except that x and y are switching roles here. So in this case, if we take a point on that line segment and we plug it into our function f, then we get f of 0y, because x has to equal 0 at all of those points. And you can check for yourself that that's equal to 2 plus 4y minus y squared. And so we know that the absolute extrema along that line segment from the origin to B have to occur at either the endpoints of that segment, so either at 0, 0 or at 0, 9, or a critical point that's inside of the line segment. And to find any critical points, we take the derivative with respect to y in this case, and we get 4 minus 2y. We set it equal to 0 and find that y has to equal 2. And so we found another critical point along the line segment from the origin to B. That critical point is the point 0, 2. And just from part B here, we've now gained 2 more points that we want to consider once we move on to step 3. So notice that the point 0, 0 we already included from part A, so I didn't list it again. But 0, 9 is a new point to consider, and then the critical point 0, 2 is a new point to consider. So we'll collect both of those points. And now finally, we look at the last segment of our triangular region. So we look at the line segment that goes from the point A to the point B, and this is the most involved, I think, of the different segments here. So the segment from A to B is given by y equals 9 minus x, a line. So the segment from A to B is just a portion of that line. And so if we take a point on the line segment AB and we plug it into our function f of xy, we get f of x 9 minus x, because on that line segment, y is always going to equal 9 minus x because of this equation right here. And if we plug x 9 minus x into the function and do a little bit of algebra, we find that it is equal to minus 43 plus 16x minus 2x squared. And again, we know that the absolute extrema for the function has to occur at either the endpoints of the interval, so either at the point A or the point B, or it has to occur at some critical value or critical point along that line segment from A to B. And to find the critical point, again, we take the derivative of f of x 9 minus x. So f prime of x 9 minus x is equal to minus 4x plus 16. And we set that equal to 0 to find critical points and find that x is equal to 4. So we do have a critical point on that line segment, and that critical point is going to be the point 4, 5. And again, we have already collected the endpoints of the segment from A to B, so we just make special notice of this new point here for part C, this critical point 4, 5. And now we've collected a bunch of different points from step 1 and then parts A, B, and C of step 2. And in step 3, we're going to take all of those points from above, and all of those points from above exhaust the possibilities for where f can have its local or its absolute minimums and its absolute extremas, or absolute maximums. And we are going to take all of those points and we're going to compare the value that we get when we plug those points into the function f. So here's just a list of the different values that we get. When we take 1, 2 and we plug it in, we get 7. We take 0, 0, or just the origin and plug it in, we get 2. When we take 1, 0 and plug it in, we get 3. When we take 9, 0 and plug it in, we get negative 61. When we take 0, 9 and plug it in, we get minus 43. When we take 0, 2 and plug it into the function, we get 6. When we take 4, 5 and plug it into the function, we get minus 11. So these are all the different values that pop out at our different points. And to find the absolute maximum of the function f, we just pick out whichever value is greatest. So in this case, that value ends up being 7. So 7 is going to be the absolute maximum. And we can also note that the absolute maximum occurs at the point 1, 2. And it looks like negative 61 is the smallest value here. So the absolute minimum for the function f over the region is going to be negative 61, and that minimum is going to occur at the point 9, 0. Okay, so this was a little bit of an involved example here, but it is important to go through the calculations that we have to do on the boundary of that region R, and this is going to show up in your homework as well. So I think that's enough material for the video, but there are many, many applications of this kind of thinking, the things that we've developed in this video. So remember from Calc 1 that right after we started talking about absolute extrema, we immediately started talking about optimization problems. And there isn't a section devoted to optimization problems now for this generalization of the material to higher dimensions, but there are problems related to optimization inside of the exercises given in the book, and I've assigned some of them for homework. So hopefully you can take some of the ideas here and use them or apply them to some more difficult or maybe more interesting problems, some optimization problems, for example. So that is the end of chapter 14. The exam is going to be handed out on Friday. Yeah, and I think that's all the information I have for this video. So you can look forward to a review video that I'm going to put out soon, and then we'll get started with chapter 15. So I'll see you then.